Hello all, I'm Dr. Rizvi and this is part 2 of our lecture on torsion equation. In the previous lecture we have solved the torsion equation and we have derived it, and now we will derive the second part of the equation for hollow circular shaft. Here you can see in the diagram that a shaft is given with two diameters, and let the internal diameter be small d, such that the internal radius is a small r, the internal radius is a small r, the external radius is capital R, such that the internal diameter is a small d and outer diameter is capital D. Here it is shown in the figure. Let tau be the shear stress. Let tau be the shear stress at a radius of capital R. Is shear stress at radius of capital R, means total radius, outer radius. We know that the procedure that we have followed for the solid shaft, that the turning moment on this elementary ring here of thickness dx at a distance of a small x from the center is equals to tau x into 2 pi x dx into x. This is the force and this is the perpendicular distance from the center. This is the turning moment that is acting on this elementary ring. Now we integrate it from the portion where the material has started. We will integrate it from small r to capital R. We will integrate the turning moment to find the total turning moment on the shaft, that is this hollow shaft. And this is from small r to capital R, tau x into 2 pi x dx into x. In the first derivation, we have also seen that tau x upon x equals to tau upon r. That means tau x equals to tau into x upon r. We will place this value of tau x here. So integration of dt will be equals to integration from small r to capital R, tau into x upon r into 2 pi x dx into x. Since tau is constant, r is constant, pi is constant and 2 is constant, so we will take out these value 2 pi tau upon r, and we will integrate x cube from small r to capital R. So the total turning moment T will be equals to 2 pi tau upon R, and this is x to the power 4 upon 4. On integration of x cube we will get this value, and we will place the limits, and this will be pi upon 2. We'll take out 4 out, we will take 4 outside, and this will be pi upon 2 into tau upon R, and in bracket capital R to the power 4 minus small r to the power 4. These are the limits. On solving, we will get t equals to pi by 16 into tau. We will make r, and we will make it d equals to 2 times r, and this will be d to the power 4 minus a small d to the power 4 upon d. This is the value of twisting moment or turning moment. We also know that for a hollow circular section, IP polar moment is pi upon 32, capital D to the power 4 minus a small d to the power 4, or it is pi by 2 capital R to the power 4 minus a small r to the power 4. This is for hollow shaft, and from here we can say that T equals to tau upon R into IP. We'll place this value, that is T upon IP equals to tau upon R equals to G theta upon L. This is the final torsion equation for the hollow shaft, and here IP is pi by 32 capital D to the power 4 minus a small d to the power 4, or pi by 2 capital R to the power 4 minus small r to the power 4. This is the torsion equation for hollow shaft. Now let us discuss torsional rigidity. This is an important term that is asked in examinations. Torsional rigidity. Torsional rigidity is basically a constant term that is represented by small k or mu. Since we know that g and the length and the polar moment are constant for a given shaft, and theta, that is the angular twist or the angle of twist, is directly proportional to the twisting moment T. So this value G into IP upon L is constant, and this is known as torsional rigidity. These three values are constant for a particular shaft, and they are represented as torsional rigidity, and they are denoted by small k or mu. So the relation is small k equals to GIP upon L, or it is equals to T upon theta, since theta, the angle of twist, is directly proportional to the twisting moment. The last topic that we will discuss here is the power transmitted by shaft. Power transmitted by shaft. This is the amount of power that the shaft transmit on application of twisting moment. Let us consider a force F in newtons that is acting tangentially on this shaft so that it start to turn, and let the radius of this shaft be capital R, and the twisting moment thus will be equals to F into R, the force into the perpendicular distance R, and it will rotate at the speed of n rpm. The shaft will rotate at a speed of n rpm. Then the work supplied to the shaft per second, work supplied to the shaft per second, will be equals to force into distance moved per second, that is F into 2 pi Rn upon 60 Newton meter per second. So the power is F into 2 pi Rn upon 60, and we know that F into R is T. It is equals to T into 2 pi N upon 60 watt. And if we want to calculate in kilowatt, So power will be equals to T into 2 pi n upon 60 into 1000, and now the value will be in kilowatt. So this is the procedure to calculate the power transmitted by shaft. T is the twisting moment, N is the speed with which the shaft is rotating. This is how you can find the value of power transmitted by shaft. That's all for the video. Thank you.